everyone, welcome to the video answer key to this worksheet on the strength of acids and bases. Now let's take a look at first A. Exercise A is all about writing the ionization equations and the acid ionization constant expression for each of the acid. So first let's do number 1. Here I have this acid, and first of all, out of our 4 steps, we need to do the first one. Step number 1 is to identify whether this is a strong or a weak acid. So this is not part of my list of 6 strong acid. Here I have it here for us to take a look at. And HClO2 is definitely not part of this list, so we know it to be a weak acid. So I'm going to do HWA for weak acid. Now let's start writing our ionization equation. Step number 2 is to write down the acid as the reactant. Now this acid will dissociate partially because it's a weak acid, and we're going to show that by writing the equilibrium or the two-way arrow. This will dissociate partially into 2 products, and the first one is always H+. And then the second product is whatever that's left, right? Now we have HClO2. If H is gone, then what we have left is just ClO2 minus. So we got that first thing done, write the ionization equation. Now we need to write the acid ionization constant expression, and that is our Ka. So as with all K expression, the product over the reactant. So the only thing we need to just make sure is that we carry our charges here of the ion so that we don't lose them or put them outside the brackets that shows the concentration. So the concentration of the product over the concentration of the reactant. Just like so. So we finished with number 1. Let's take a look at number 2. Now number 2 is HNO2. Once again, let's look at our list. It is not part of a strong acid list, so we have once again a weak acid. Let's go ahead and start writing the ionization equations. HNO2, because it's a weak acid, it's going to dissociate partially, and we're going to show that by using the equilibrium or the two-way arrow. This will dissociate partially into 2 products, one always being an H+. The other product then would be whatever is left over from the acid, which is NO2 minus. Let's write our acid constant expression just like that. Let's do number 5, permanganate acid. So we have to translate that into a chemical formula, and there's no hydro in our name. That means that the chemical formula definitely has an oxygen. And in fact, I know that the permanganate anion is MnO4 with a minus charge. Now with all acid, we're going to start with a hydrogen, and the hydrogen is always a plus charged. So let's bring this charge down like so, and we have our final chemical formula to look like that. Then let's determine whether that's a strong or weak acid. It's definitely not part of our 6 strong acids, so it has to be a weak acid. So here is my weak acid showing the equilibrium arrow, and then this just dissociates into 2 things. One is your H+, and the other thing is whatever that's left, which is MnO4 minus. Alright, let's write our Ka expression. Now go ahead and use the skills that you just learned from watching me do 1, 2, and 5 to go ahead now and complete 3, 4, and 6. Let's take a look at exercise B, where they ask you to do the same 2 tasks but for a base. So let's look first at ammonia. The first step is always to identify whether the base is a strong base or a weak base. Now ammonia is not part of our 6 strong bases here. A really good way to remember if the bases are strong or just strong bases have hydroxide in it. So ammonia definitely does not have hydroxide, so we know it's a weak base. I'm going to write that's a weak base. So let's start writing down the ionization equation by starting with the base in aqueous form. And then we're going to, the other reactant is water, that's in liquid form. And because it's a weak base, we're going to draw the equilibrium arrow to indicate the partial dissociation. Then one of the two products must be OH. And the other product would be whatever it is made by this base gaining a proton. So when NH3 gains a proton, aka it gains an H+, it would make an H4. Now the charge has also changed, going from neutral in ammonia to a +1 in ammonium. There's also one thing I've forgotten here, which is both of these must also be in aqueous form. So now let's do our Kb. Remember that the ionization constant for bases, or Kb, and then the ionization constant for acid, or Ka. So for whether it's Ka or Kb, we do the same step, where the top would be the concentration of your product and the bottom would be the concentration of your reactant. So here is a concentration of your product. Make sure that your charges are contained within the brackets. Do not write the phases into your equilibrium expression, meaning that the aqueous or the liquid, do not write it into your equilibrium expression. And then the bottom is ammonia concentration. And there you go. Let's move on to number 4, where here I have just a carbonate ion. So a carbonate ion, it's not part of the strong base list, so we know this to be a weak base. Let's start writing it down here in aqueous form. And the other reactant must be water. And then to show the partial dissociation, we're going to use the equilibrium arrow. And then that should give us two products, one of which is an OH minus, aqueous, and the other product must be whatever is produced when the carbonate ion here gain a proton. So if it gains a proton, it becomes HCO3 minus. Now how did I get this minus sign here, or the -1 sign? This is because of this reason. Initially, our carbonate ion has a charge of -2. When it obtained a proton from the acid, in this case it's our water, it obtained, in mathematical terms, is a plus. -2 plus a proton, and a proton, the charge is a +1. So -2 plus 1 is -1. And that is why the charge of this ion is -1. Let's write now our Kb expression. Like always, the product at the top and the reactant at the bottom. As you notice, for both number 1 and number 4, I do not include liquid water in our equilibrium expression because that's just not something that count towards our equilibrium. So it doesn't affect the equilibrium of the reaction, hence it doesn't belong in the expression. Let's go ahead and go through number 6 together. So barium hydroxide. Here, barium hydroxide, it's definitely one of our strong bases because it has the hydroxide in the chemical formula, and we know that all strong bases have hydroxide. So this is a strong base. Now when you have a strong base, you are going to do things a little differently. When you have a strong base, the reactant start with just a base in solid form. So I'm going to start with barium hydroxide as a solid. And then because it's a strong base and it dissociates completely, I'm going to show that by writing down the one-way arrow. Now barium hydroxide will dissociate into OH minus, aqueous, that should always be one of our two products, and the other ion, which is barium +2. This is also in aqueous form. Now this is one of those situations where you do need to balance your chemical equation. Here I have one barium on one side, and then I have 2 hydroxide on the other side. So I'm going to need to balance that out by writing the number 2 in front of the hydroxide ion in order to balance this chemical equation. Now, how did I know that barium is a +2? It is because we know that barium is part of group number 2 on our periodic table, and group 2 produce ions with the charge of +2. So that's how I got that charge. Now, what about Kb? Well, Kb is actually not applicable to strong bases because there's actually a different equilibrium constant for this kind of reaction, but we are not going to cover that in this module, so you don't have to worry about it. So all I'm going to say here is that no Kb because barium hydroxide is a strong base. So Kb is only applicable to weak bases. So there's no Kb there. Now go ahead and use these problems as a model for you to do number 2, 5, and 3. Now I want to go over part C just a little bit. So I'm not going to give you the full answer for... Let's take a look at part C, where I give you a chart of different acids of varying Ka values. And I want you to analyze these values to predict the relative strength and also conductivity of these different acids. So first of all, number 1, the purpose is to basically remind you of what it means by when you have a higher Ka value and a lower Ka value. So weaker acids have, so let's tackle 1A. Weaker acids have a small or bigger Ka value. Now as a reminder, Ka is like all K has the product on the top and the reactant on the bottom. As we know, because weak acids don't like to dissociate, they only dissociate partially, what you have for a weak acid is more reactant than a product. So more concentration of a reactant than your product. Well, what does this mean for Ka? If you have a bigger denominator, here you would have a smaller overall Ka value. What this also means is weaker acids will then have a smaller Ka. Now the exact opposite must be true, so vice versa. Stronger acid then should have a bigger Ka, which also does make sense because stronger acid, so here I'm going to write this here also, strong acid, more product than reactant. If that's the case, then we have a bigger numerator up here, and that should give me a bigger overall value of Ka. Let's look at C. Weak acids are poor or good conductors of electricity. Well, remember that the more ions you have in the solution, the better the conductivity is. So weak acids dissociate only partially, meaning that there's not a lot of ions floating around, and that would make it a poor conductor of electricity. So I'm going to say poor, and then vice versa, strong acid would make good conductors of electricity because more ions. So actually just write this down so then we can use that as a reference. E and F. For E, smaller or bigger Ka would then means the acid is a better conductor of electricity. So E and F basically combines the information in A, B, C, and D. If the acid is a better conductor of electricity, that means that it's more likely to be a stronger acid, right? Because if it's a better conductor, meaning it has more ions floating around. Now, what does coincide with stronger acid in terms of Ka value? We know that stronger acid from B would have a bigger Ka value. And so this would be my answer, bigger Ka. F. Ka value means the acid is a poor conductor of electricity. Well, if it's poor, that means that it has less ions in the solution, and that would mean that it's a weaker acid. And what kind of Ka value corresponds with a weaker acid? Something that's a little bit smaller, just like how they said in A here. So then my answer is small. Now, knowing these relationships between your Ka value, the strength of the acid, and also how well the acid is at conducting electricity, go ahead and analyze these numbers up here and then do your ranking for number 2, which is asking for increasing strength, going from weakest to strongest, and then number 3 is where it asks you to rank it in terms of increasing electrical conductivity, meaning the worst conductor to the best conductor of electricity. I'll leave that to you to attempt, and thank you so much for your attention through this video answer key, and I will see you in class.